Okay, so let's run through a couple of examples applying the sticks and stones here. Now, I do want to just kind of focus on one of these problems in the textbook that we use, mainly because, so let's take a look at the problem here. So it says your favorite mathematical ice cream parlor offers 10 flavors. How many milkshakes could you create using exactly six, not necessarily distinct scoops? The order you add the flavors does not matter, they will be blended up anyway. But you are allowed repeats. So one possible shake is triple chocolate, double cherry, and mint chocolate chip. All right, now I do just want to point out something in the solution here. I think not I think, earlier in the reading here, he introduces different methodology in terms of like stars and bars. Again, really just two symbols. I'll stick to the sticks and stones method, just because I've been using in previous videos, but it does get confusing here because he starts off calling them star, and then here later he uses three stones in his description here. So just wanted to give you guys a heads up here. I think that's just a typo. He kind of skipped. He alternated between the different terminology that he was using. So I'll stick to the sticks and stones method here, and let's run through the solution here. All right, so the problem tells me that I have six. So I have six scoops to work with and 10 flavors. All right. Okay, so here 10 flavors and six scoops. Okay, we can think of the scoops as being identical. Right, and we each got just six scoops of the same size here. The flavors what alternates, right? And we can think of placing these scoops into the flavor bins, right? So we have six scoops here. So we have 1, 2, 3, 4, 5, 6. All right, and we have 10 different flavors. Now, obviously, we're not gonna have a scoop of all the flavors. So let's say in our first spin was chocolate. I can put a stick there. All right, now as I walk through and then maybe I want to skip some flavors in here, I can do stuff like that, right? And then this one, I want 2 scoops of that. All right, and again, we can skip here. Okay. Okay, so we could see there what this corresponds here when you have multiple sticks kind of next to each other is that, think if you're walking through the case of flavors, you just skip some of them, right? Because you're not going to use them. So they have no stones here in our little diagram here. All right, so the bins are empty, right? We can think of this as chocolate bin, strawberry bin, whatever you want, whatever flavors we can imagine here. Okay, so if we think of K being the the scoops, right, and the bins being the flavors. All right, so then we have here in our formula, we have NK plus N minus 1 here, and then all over K. So that turns out to be 15 choose 6. So we have 5005 different combinations here. All right, so that's one way to think of these multi-set problems, right? So multi-set of size K, distributing these K objects, here in this case being the scoops, into N distinct bins. Now another interesting kind of way to think of some of these problems here, right, is, and let's say we had the solution, an equation and I want to find non-negative integer solutions to the following, to the equation up here, right? To x1 plus x2 plus x3 plus x4 plus x5, right? So one way to think of this right now, it is specific to a non-negative integer solution. So it can be 0 through 1 through 2. Now there's a cap into what these values can be, right? Like, so x1 can be 13 only if the rest are 0, right? Or x4, any one of these can be 13 and the rest being 0. Or we can kind of split across different numbers there, right? Like 2, let's say if they were all 2 plus 2 plus 2 plus 2, what's 8? So that means that x5 would have to be 5, right? So now one way to interpret this is we can think of our objects here as being just the stones that we have 13 of them, right? Just each representing having a value of 1. Okay, and then the bins represent the quantity of our variables, right? x1, x2, x3, x4, x5, right? So then I'll have, if I have 5 bins, I'm gonna need 4 sticks, right? You can think of the sticks almost representing those plus signs, right? So if you kind of displace them out here, like this, right? Then we can think of this as my x1, x2, x3, x4, x5, right? And we can just add them up right there. Right, you see the 13, and now this represents one non-negative integer solution, right? And then how many different solutions I have, or it's how I can distribute these 17 symbols, right? Almost like our bit strings. So to find the total ones, that would be 17, choose 4, right? So we have the 13 objects here, and then 4 to 6, excuse me. So that would be 17, choose 4. That is a total of 2,380. 2,380 different solutions. All right, now we can modify our problem where we can make a variation of, maybe we make the specification of at least 1. So let's say we had, going back to our cookie problem, right? So let's say we want to distribute 7 cookies to 4 kids. So each kid gets at least 1. Okay, all right. And then from here, what you want to do for something like this, right? If we have each one gets 1, then right away what you want to do is you want to subtract off the 4 that you'll give 1 to each kid, and that leaves 3 cookies to play with, right? To distribute among the other 4 kids. Okay, so we have 3 stones, right? Our objects here are identical objects here, and then the bins represents the kids, so we need 3 of them, right? So we have 1, 2, 3, right? So here in this formulation, not everyone's gonna be able to get 2, right? And then you can have a formulation where some of them do get more than 2, right? If we add something like this, right? So that is allowed too, right? So if we do that, then we have, in this case here, we have using our formula, right? Still with the 4 kids, 3 sticks, so 4 plus 3 minus 1 is 6, and I want to choose 3 of them, right? So for a total of 20. 20 different arrangements where each kid has at least 1 cookie here. All right, so that's how we use counting multi-sets, right, where we allow repetition of identical objects.